In this video, we present R plus X, Retrieval and Execution from Everyday Human Videos, published at ICRA 2025. In this work, we study the problem of learning robot skills from long unlabeled first-person videos of humans performing everyday tasks in everyday environments. By this, we mean that a user can wear a camera and record how they naturally interact with their environment during the day. There is no need to label what the tasks are or to manually cut the video. With this setup, we record natural interactions around multiple environments, emulating many everyday tasks a person might do. We will now show how we can translate these videos into robot behaviors. Once we've collected hours of videos, how can a robot emulate such behaviors when no robot data and no task labels are available? To tackle the lack of robot data, we first pre-process the videos by extracting the hand pose in 3D for each frame and translating it into gripper poses. This method is remarkably robust and works in many settings and environments. When the robot now receives a new command, we retrieve the relevant videos at test time and use an in-context imitation learning method to execute the behavior on the spot. For example, given this long unlabeled human video, let's say the robot is asked to pick up the phone. Even without any labels, we can query a vision language model like Gemini with a command and ask it to extract all the relevant clips from the long video. This is the retrieval phase. Given these videos, we represent both the observation and the actions as key points that we can then feed to our in-context imitation learning method. We do this by extracting dino features from the first frames of all retrieved clips, and then extracting k-patch descriptors via a nearest neighbor-based matching method that allows us to find these key points in new observations. This approach is very robust to different environments and settings and generalizes to different objects of the same class. So after retrieving the videos, we now have a set of key points representing the observations, and we can represent the hand poses as key points of the fingers too, that we call hand joints. We now enter the execution phase. We give these points as input to key point action tokens, a language model powered in-context imitation learning method, without the need to train or fine-tune policies. We then provide the key points extracted from the current observation, and CAT can generate, on the spot, a new trajectory of hand joints that we can translate directly to robot movements. In summary, through retrieval and execution with in-context learning, our method can emulate the behaviors seen in the videos without the need for labels, robot data, or training. Besides this, what are the advantages over training a single language condition policy? We tested our method on 12 everyday tasks and found a series of interesting differences with respect to monolithic policies. We test these differences through 3 main generalization tests. The first is hard language generalization. We provide to our method and to R3M and Octo, 2 baselines, language commands that were never seen before. Our method is strongly better at handling unusual wordings of tasks, thanks to the power of the underlying VLM still retrieving the relevant clips. The second is hard spatial generalization. We place the target objects in locations never seen in the demos, like a can on top of a microwave. Thanks to the extraction of visual key points and our LLM-based imitation learning method, R plus X retains strong performance also in these situations, while R3M and Octo struggle with out-of-distribution situations. Finally, we test for distractors generalization. As shown before, thanks again to the key points extraction phase, that is robust to different scenarios and distractors, our method is more robust to distractors than the baselines. Additionally, another difference with respect to training policies lies in the performance in continual learning. Policies need to be fine-tuned when new tasks are added, but performance on past tasks often deteriorate. An advantage of retrieval and execution within context learning is that there is no need to retrain, even when the amount of available tasks and videos increase. An additional benefit of the lack of training is that there is no degradation in performance on past tasks. Our method has, however, a series of disadvantages over monolithic policies. The retrieval phase introduces a certain latency in execution. Additionally, key points, while providing many advantages, can also miss visual cues from the observation. Finally, there is a lower ceiling to the dexterity of tasks we can execute with respect to training a neural network as a policy. Thank you. Visit our website for more details and code.